All right, so now that we know that light is quantized from the previous video, we can explain the problems that were encountered with this second experiment that I mentioned. It's called the photoelectric effect. And the person who solved this problem was Albert Einstein. I'll explain the problem in a second, but first just want to tell you, Albert Einstein, obviously, if you had to choose top most famous scientists, probably you choose Albert Einstein, I think, although there's so many. But a lot of people think of him for his work on general relativity and special relativity and sort of, outer space type phenomenon, right? Large scale phenomenon. He actually got the Nobel Prize for figuring out the photoelectric effect, okay? And arguably this is actually more important because it dealt with quantum mechanics, okay? And so what is the photoelectric effect? What it is at the most basic level is you're gonna take a piece of metal. Metal's the most common material used here. So here I show sodium metal. And you're gonna have light in the form of photons shining down at this surface. So photons are the particles that make up light. We'll talk about that more later. But basically you just are shining light on a metal, okay? And so this could be a laser, it could be a lamp, whatever. We'll like to think about it as a laser because a laser is one color of light, so it's easier to think about. But when you do that, you, under certain circumstances, will get electrons being ejected from the surface of that metal, okay? And so the metal will become positively charged. If it's becoming positively charged, remember that means that it is forming cations, okay? Because negatively charged electrons are leaving the surface of the metal, all right? So this was a strange thing, was that when you did this experiment, it didn't matter what the intensity of light was that you used in order to get electrons to eject off the surface. So let's say you have a sodium metal and you shine red light at it, okay? You shine a weak red light laser on sodium metal, and in this case, nothing will happen. You'll get no electrons, okay? So according to classical physics, if you took a powerful laser, a very, very powerful laser, so you get a huge honking red laser, and you shine that light, very, very bright red light on the sodium metal, you would then expect to get electrons emitted. But if you do the experiment, you don't, okay? And you just never get electrons coming out. It doesn't matter how powerful that red laser is. You have to use a different color of light in order to get the electrons out. And that is because different colors of light have different energies. So in this case, you have to use a higher energy color, like blue light or ultraviolet light, okay, that has more energy. And then even if you're shining a really weak ultraviolet laser or really weak blue laser, because the photons, the particles of light in that laser have more energy in each particle, you will get some electrons ejected, okay? Regardless of the intensity. Now, of course, if you use a big honking ultraviolet laser, you're gonna get more electrons. But if you use a very weak ultraviolet laser, you're still gonna get electrons. So that threshold at which we make electrons doesn't depend on intensity. It depends upon the color of light, the wavelength of light, the energy of light, the frequency of light. All those things are interrelated, as we'll talk about in the next video. Okay, so that's the photoelectric effect, fundamentally. And so this is getting into now, how to calculate the energy that a photon has. And we have to use this equation here. Energy of the photon equals h Planck's constant times c divided by lambda. Lambda is the wavelength. Okay, we'll go over this later in other slides. C is the speed of light, about equal to 3 times 10 to the 8th meters per second. And h is Planck's constant, which we went over. It's also equal to E is equal to h times nu, and nu is frequency, remember? And so there's a relationship between wavelength and frequency. C equals lambda, or wavelength, times nu. Okay, so speed of light equals wavelength times frequency. And we'll be doing problems on that in a second. So basically, if summarizing the photoelectric effect is as follows down here at the bottom. If the energy of the photon isn't enough compared to the E naught, okay, E naught is the minimum energy required to eject an electron from the metal surface. Physicists call this the work function of the metal. So if the photon doesn't have enough energy, then the electron won't be ejected, okay? And if there is enough energy, then the electron will be ejected. So if there's greater energy, then the electron will be ejected. All right, so that's basically that explanation of the photoelectric effect. Next video, we'll go over this problem with respect to the photoelectric effect. All right, and that's it.